Hello friends, today we will discuss some solve example from GTU question paper. Before we start to solve the examples, first of all we will revise certain things so that you can easily solve the examples. So let's start with the revision of the fundamentals of AC circuits. First is the DC quantity. As we were discussing last some sessions, that DC quantity is the quantity in which the magnitude and the direction of a given quantity remains constant throughout the time period. Means magnitude and direction is constant for a given quantity throughout the time period. And if you to define a AC quantity, then AC quantity is the quantity in which the direction and the phase angle, or you can say the magnitude and the direction of a given quantity changes with respect to time. So this is the basic difference between DC quantity and AC quantity, that in DC quantity magnitude and direction both remains constant, while in AC quantity direction and magnitude both will change with respect to time. Now next is the certain definitions related with the alternating quantity. First is the cycle. Now cycle is the set of positive, negative and zero values of alternating quantity. It is known as a cycle. Second is the amplitude. Amplitude means the peak value of alternating quantity, or you can say the maximum value attained by any alternating quantity. It is known as a amplitude. Third one is the frequency. Frequency means number of cycles passes per second for given alternating quantity. It is known as a frequency. Then next is the instantaneous value. Instantaneous value means the magnitude of a alternating quantity for a particular instant is known as a instantaneous value. So the value of a alternating quantity changes with respect to time, then the instantaneous value of alternating quantities also vary with respect to time. Fifth is the phase. Phase is the fraction of time period elapsed by any alternating quantity from the last pass zero value. Okay, suppose you are consider 0 as a reference value, then the phase is the difference from the 0 value to a particular point from which you have to find a phase of alternating quantity. So it is nothing but the fraction of time period, and it is calculated from the last pass 0 value. Sixth one is the RMS value. Now RMS value is related with the amount of heat produced by a given current. Suppose you are having one circuit and you are giving a DC current to a particular circuit. Due to this current, some amount of heat will produce. Now if you are passing a AC current from the same circuit for a same particular time, and if it is produced same amount of heat which is produced by DC, then this value of current is known as the RMS value of alternating current. So when you have to define RMS value, you have to concentrate on amount of heat. So the RMS value is directly proportional to the square of current, because heat is equal to I square R. So RMS value is directly proportional to the square of the current. Next is the average value. Now when you have to define an average value, you have to concentrate on the amount of charge. Suppose you are having one circuit and DC current passes through the circuit. Due to this, some amount of charge will pass. Now if you are replace this DC current by AC current, and if it is produced same amount of charge, then it is known as the average value of a alternating quantity. So when you have to define an average value, you have to concentrate on amount of charge. So charge is equal to Q. Now as we know, I is equal to dQ by dt. So whenever you define an average value, your average value is directly proportional to the amount of current, while RMS value is directly proportional to the square of the current. Now next is, it is a form factor. Form factor is the ratio of RMS value by average value. As we discussed in last some session, that RMS value is 0.707 into Vmax and average value is 0.637 into Vmax. So form factor is the ratio of RMS value and average value. You can use this equation to solve certain examples. Next is the peak factor or crest factor. The crest factor is also a ratio of peak value, or you can say the maximum value, to the RMS value. You can use this relation to solve certain examples. And next is conditions for vector representation. As we discussed that any alternating quantity is represented by a vector if you are satisfy certain conditions. Mainly 3 conditions are there which you have to satisfy. First condition is that the rotating vector should be equal in magnitude to the peak value of the alternating quantity. So the rotating vector and the peak value, or you can say the amplitude of alternating quantity, should be same. Then you can represent a vector as a, and second condition is that the vector should initially start from the 0 and then move in its positive direction. As we know, alternating quantity is start from the 0 value and then increasing, goes to the maximum, and again decreasing, come to the 0 point. It may be start from 0, decreasing, goes to the negative maximum value and come back to 0. But if you have to represent any alternating quantity as a vector, then this vector should be initially start at 0 and then moves in a positive direction, means anti-clockwise direction is preferable. If you are reverse the direction, it will indicate that the direction of alternating quantity is also reverse. And the third and last condition is that the speed of the rotation of the vector should be such that when it completes one revolution, the alternating quantity completes one cycle. So the angular speed of the vector should be exactly equal to the frequency of the alternating quantity. So whenever your vector completes one revolution, your alternating quantity complete one cycle. If you are satisfied these 3 conditions, you can represent any alternating quantity by a vector quantity. Now next topic is polar form. If you have to represent alternating quantity in form of a vector, then 2 forms are available. First form is the polar form, second form is the rectangular form. Polar form is where complex number is denoted by a length known as the magnitude and the angle of its vector. So if you have to represent alternating quantity by a vector quantity, first choice is your polar form. So find the magnitude or length of the given quantity and find the angle. You can represent it in a polar form. Second is the rectangular form. In rectangular form, complex number is denoted by its respective horizontal and vertical components, or you can say in rectangular form your quantity is represented by a real part and imaginary part. Your real part is the horizontal component, imaginary part is your vertical component. If you are make the combination of these 2 components, your quantity is represented in a rectangular form. So 2 forms are available. First is the polar form and second is the rectangular form. If magnitude and phase angle is known to you, you can represent it in a polar form. If real part and imaginary part is known to you, you can represent it as a rectangular form. So 2 forms are available to representation of alternating quantity. And the next topic is RL circuit in series. Now as shown in figure, resistor and inductor is connected in series and the alternating supply is given to a particular circuit. Whenever this type of circuit is there, the voltage and current relationship is like that. If your current passes through the resistance, then this current is always in phase with the voltage. But whenever current passes through the inductor, your current is always in a lagging behind the voltage by 90 degree if it is purely inductive circuit. But if you are make the combination of R and L, then the resultant is your current is lagging because inductor is there. So your current is lagging, but not exactly at 90 degree because it is a combination with resistance. So the phase angle between voltage and current is between 0 to 90 degree. It depends upon the value of resistance and value of inductor. So when it is RL circuit, your current is lagging and your phase angle is between 0 to 90 degree. Now next is RC series circuit, when resistance and capacitor connected in series and one alternating voltage is connected with this combination. Now as we know, in capacitive circuit, your current is always leading by 90 degree to the voltage, but it is the combination of resistance and capacitor. So the phase angle between voltage and current is between 0 to 90. It is leading, but it is not exactly 90 because it is RC combination. So your phase difference between voltage and current is between 0 to 90 degree. Definitely current is leading by the voltage between this region 0 to 90 degree if it is RC series circuit. Now RLC series circuit. So as shown in figure, this is RLC series circuit. voltage across resistance, voltage across inductor and voltage across capacitor is denoted by VR, VL and VC. Now if you have to find a voltage and current relationship for RLC series circuit, so it is depends upon the VL and VC. If voltage across inductor is higher than voltage across capacitor, then it will indicate that it is an inductive circuit, and if VC is higher than VL, then it will indicate it is capacitive circuit. So the voltage and current relationship of RLC series circuit is depends upon the magnitude of inductor and magnitude of capacitors. If XL is higher than XC, then it is inductive circuit. If XC is higher than XL, then it is capacitive circuit. If it is inductive circuit, your current is lagging, and if it is capacitive circuit, then your current is leading. So the voltage and current relationship for RLC circuit is depends upon the value of XL and XC, and it is represented by impedance Z, which is equal to R plus JX, where X is XL minus XC or XC minus XL. So whenever you have to find the relationship between voltage and current for RLC series circuit, you have to find the impedance for a given circuit, which is Z, and after finding Z you can find the relationship, or you can say the phase angle between voltage and current. Now next is the series resonance circuit. Now this is again RLC series circuit. Voltage across resistance is VR and voltage across inductor and capacitor is VL and VC. If XL is equal to XC, then what happen? Voltage across VL and voltage across VC is same, so it will nullify the effect of each other. So your circuit is represented like this. This is the circuit at the time of resonance. So this line indicates that L and C component are short circuited, means no effect by these two components. So the net X is equal to 0 because XL is equal to XC, so XL minus XC is equal to 0. So this circuit behaves like a resistive circuit. Only resistance is connected in the circuit. So at the time of resonance, when it is a series circuit, at a time of resonance, the impedance of a given circuit Z is equal to R. So value of Z is minimum. So you can say at the time of resonance, the current passing through the circuit is maximum. So this is the representation at the time of series resonance. Net reactance of the given circuit is 0. Now parallel resonance circuit. So again it is a parallel combination of resistance, inductor and capacitor. R, L and C is connected parallelly and alternating supply is connected with this. When resonances occur, then this effect of these two elements are 0. So it is represented by an open circuit. So this block indicates the open circuit at the time of parallel resonance. So your equivalent circuit is again a resistive circuit. So whenever parallel resonances occur, net value of X is equal to 0 and circuit is purely resistive circuit. So this is the equivalent circuit for a parallel resonance. Now we are solving some examples from GTU question paper. Your first example is two impedances Z1 is equal to 10 plus J15 ohm and Z2 is equal to 6 minus J8 ohm are connected in parallel, and this combination takes 20 ampere. Find the supply voltage. This example was asked in December 2010. Two impedances are given to you, Z1 and Z2, and the total current passing through this two combination is also given. You have to find the supply voltage for this particular combination. The figure is shown. Z1 and Z2 connected in parallel, and the combination of these two will take 20 ampere currents, and you have to find the value of voltage. Okay, Z1 is equal to 10 plus J15. Whenever you find a value of admittance, then Y1 is equal to 1 upon Z1. Value of Z1 is given, so it is 1 upon 10 plus J15. So it is 1 upon 10 plus J15 multiply with the conjugate number, so into 10 minus J15, 10 minus J15. So it is like this, 10 minus J15 divided by 10 square plus 15 square. So your Y1 is equal to 10 minus J15 divided by 325. If you are simplify this equation, so your answer is 0.030 minus J 0.046. This is the rectangular representation. You can convert this into a polar form. So for that, first of all, find the magnitude of this. So it is equal to under root of x square plus y square. So you can find the magnitude, which is 0.03, and your phase angle, which is equal to tan inverse y by x. So tan inverse 0.046 divided by 0.030. So your angle is minus 87.79, and the unit for admittance is mho. So here it is mho. So this is the value of Y1 for a first branch. Same way you have to find the value of Y2 for a second branch. So Y2 is equal to 1 divided by Z2, which is given, is equal to 1 upon 6 minus J8. Again multiply with the conjugate number. So it is 6 plus J8 upon 6 plus J8. So your Y2 is equal to 6 plus J8 divided by